Okay, so at this point we've talked a little bit about galvanic cells, as redox reactions, how these are pertaining to batteries. What's one thing that we know is sort of intimately related to a battery? It would be voltage. And we haven't spoke of voltage yet, and now we're going to see how that plays into these different cells, how that also pertains to spontaneity. And so traditionally or historically, that voltage that we have in a cell is considered the electromotive force. And so that is just basically the force that pushes the electrons away from the anode and to the cathode. It's also given us the cell potential or the cell voltage, and that's what we really should view it as more so as just the cell voltage. And the cell voltage is going to be expressed in volts, and that's just denoted by a capital V. And we should remember, will come in handy later, that 1 joule is equivalent to 1 coulomb times 1 volt. And 1 coulomb is an amount of charge that's transferred when a current of 1 amp or 1 ampere flows for 1 second. So again, how do we determine or relate the spontaneity of a cell to the voltage that we're going to measure in a galvanic cell? Well, it's delta G equals minus NFE. And we'll explain all those values in just a second here. E is, of course, the cell voltage. The value N is the number of electrons that are in the reaction. So we'll look at the balanced reaction and we'll determine how many electrons are being transferred in that balanced reaction. That'll be our N value. The F value is Faraday's constant, and it's given by 96,500 coulombs per mole of electrons. So that just represents the charge of 1 mole of electrons. And like I said, E is that cell potential. And what we're going to see is if the cell potential is greater than 0, then we're going to end up with a delta G that's less than 0, and the reaction is going to be spontaneous. We are going to represent the standard cell potential as E with the degree sign, just much like we did standard Gibbs energies, standard enthalpies of formation. All those standard somethings usually got a degree to indicate they were representing standard states. And so if we're saying they're in their standard states, what we are implying is that if we're talking about solutes, they're at a molarity of 1 molar. And for gases, they're at a partial pressure of 1 atmosphere. If we're talking about solids and liquids, we expect them to be in their pure form. And all this should be done at some specified temperature. That's usually 298 Kelvin, but could be different for different fields and places, areas of study. Okay, so now let's take a look at how we can identify what delta G is if we know the cell potential for 2 reactions here. I'm going to start out with a real familiar reaction. We're just going to look at the reaction of zinc and copper. And we're going to say that at 25 degrees Celsius, we measure the standard cell potential to be 1.10 volts. So we want to calculate the delta G. And the best thing to do is just make sure that we understand what N equals in this case. And it's going to be 2. Since the zinc is losing 2 electrons, the copper is picking up 2 electrons. We got the E naught value, that's 1.10 volts. And we have the temperatures at 298 Kelvin. And so we plug in all those values and we get minus 2 moles of electrons times the 96,500 coulombs per mole of electron, that's Faraday's constant, times 1.1 volts. And we come out with a value of negative 2.12 times 10 to the 5 joules, or negative 212 kilojoules, negative 212 kilojoules. And so this is a quite spontaneous reaction that we're seeing here. One other thing, just remember that the coulombs times a volt is the joule, so that's where it's important to keep in mind that gives you a joule. Another thing is just to pay attention for, if we think about Faraday's constant, that value is just a constant. It's not going to limit our sig figs. What about the sig figs that are on the moles of electrons? So the n equals 2 value. Well, that's a counting number. And so counting numbers are not going to limit you. So don't put just one sig fig because you always get one there. Go ahead and make sure that you go off of the voltage, and that's just got 3 sig figs, so we end up with 3 in the answer. So let's look at another reaction because this can be a little bit tricky. So we have aluminum and zinc reacting, and we have 2 aluminums going to 3 plus, and we're getting 3 zincs out of it, and we get a cell potential of 0.9 volts at 25 degrees C. Well, so the one thing I want to point out is the zinc is going from zinc 2 plus to zinc, so it's obviously each zinc is picking up 2 electrons. The aluminum is going from aluminum to aluminum 3 plus, so it's losing 3 electrons. So which one do we choose, a 2 or 3 for that N value? Well, we have to look at the actual reaction here, and if we look at the half reactions, and we have 2 aluminum going to 2 aluminum 3 plus, and we get 6 electrons, and we get 6 electrons plus 3 zinc 2 plus to go to 3 zinc. So you have to look at that balanced reaction when you added it up and you've had it to where you can cancel out all the electrons. That's going to be your value for N. And so since we have to exchange 6 electrons in order to balance this, then N equals 6 for this particular problem. So we plug that in, we get negative 5.2 times 10 to the 5 joules, or negative 520 kilojoules in that case. So this one asks, what's the standard Gibbs free energy for the cell depicted to the right, and whose standard cell potential is 2 volts at 298 Kelvin? So again, we're looking at a reaction where you have 3 copper and 2 aluminum reacting to give you copper metal plus aluminum 3 plus. So how many electrons are transferred in this? Well, it's the same as that problem we just did. And if we looked at what was necessary to actually balance that, that would have been 6 electrons. So this one we should get an N equals 6. And then we go ahead and calculate the delta G, and we'll find that we get negative 1160 kilojoules. Does this match up with any of the ones that we see there on the left? It does. It is B. Okay, so looking at standard reduction potentials, we've looked at standard, like I said, Gibbs free energy, enthalpies of formation, things of this nature. And basically standard reduction potentials we're using are very similar to those same things we had for delta G and delta H and so on in the past. And so we're going to basically look at a standard electrode that we typically use to measure these things reference to, and determine how we can find all these standard reduction potentials for all kinds of different reactions that could occur. Okay, so let's look at this reaction to sort of get a sense of how we're going to figure out all these standard reduction potentials. So for our half reaction of oxidation, or the reaction that occurs at the anode, we're going to look at hydrogen going to 2H plus 2 electrons. For the reduction or the cathode half reaction, we're going to look at copper plus 2 electrons going to copper. This gives us the overall reaction you see there. If we want to figure out what the cell potential is, it's just going to be the voltage of the cell is going to be the oxidation plus the reduction. And if we put it in more explicit detail, the oxidation is the H2 going to H plus, the copper 2 plus going to copper. And so we add those up and we get a value of 0.34 volts. One of the key things is we could measure this difference and we could determine it, but we don't know absolute values for these things. And so we always have to measure these cell potentials that relative to one another. We can't measure these absolute values. And so that's perfectly fine. It's not as much of a problem as one might think at first. The thing is, we just have to make a baseline. We have to find some half cell potential that we're going to just say is 0, and we'll compare it to all these other cell potentials relative to this just one reaction. And as long as we know that reaction is defined as 0, then we can determine all these other things, right? And so you might think this concept sounds a bit foreign, but it's exactly your idea of elevation. It's really no different. When we say something's at 7,500 feet, like we're in Alamosa, we're at this height or elevation. Um, well, does that mean we're 7,500 feet from the sun? Does it mean we're 7,500 feet from the center of the planet? Where does it 7,500 feet mean? Where's it reference to? Well, it's sea level, right? We use sea level as this zero level for us. And we don't even think about it that much. But we're looking at a relative scale whenever we talk about elevation. And so as long as we keep that elevation of sea level as our standard, then I could take two different points, one at 5,000 feet and one at 7,500 feet. And I know the difference is 2,500 feet because I know everything's using the same standard uh, of having sea level as 0 feet. And that's what we're doing with our reactions here. We're just going to use one of these reactions. You're going to see it's the hydrogen cell that we're going to use to just say that it is at 0 voltage for that half cell or half reduction potential. And then we're going to be able to compare all the other reactions with that. So we just have to put it in a cell with that hydrogen electrode, and we'll be able to basically figure out what that voltage is for that. And as long as everybody's using hydrogen as a baseline, we can have a system that's much like elevation to figure out what everything is relative to this hydrogen half reaction. So in this slide, we see the standard hydrogen electrode, and the standard hydrogen electrode, sometimes abbreviated SHE, is traditionally used as our reference electrode. And so in effect, this thing is our sea level reference cell, okay? So this is the thing that we measure all other reduction potentials relative to. And by doing so, we can find out what their voltage is. And so just like a measurement for sea level is 0 feet, the half reduction potential and half oxidation potential for the standard hydrogen electrode is 0 volts. And so if we look at just the reduction, we get 0 volts here. We look at the oxidation, it gets 0 volts. And so that's important for our reference that we're using here. And if you look at the cell that's below and on the right hand side where we're looking at that standard hydrogen electrode, you'll notice it does have to use an inert electrode since it's a gas, and we just bubble through the hydrogen right over that electrode at 1 atmosphere. And these types of reactions, like the standard hydrogen electrode, is usually chosen as references simply because they're reliable and they're stable at a particular temperature. So this is what we use as our standard to measure all the other reduction potentials relative to. So let's look at another reaction here. So we're going to look at hydrogen and copper here. And so we have the hydrogen being oxidized in this case, and we have the copper being reduced. We get the overall reaction there, and we know that the voltage of the cell is just going to be the sum of the oxidation half potential and the reduction half potential. And so we find that the voltage between the two was 0.34 volts, just as we did 2 slides ago. But at that time, we didn't have a solid number for either of these, so we just knew the difference. But now that we've established a value for the oxidation or the reduction potential of the hydrogen, in this case we're interested in the oxidation as it serves as the anode, but we set that value to 0. So it becomes 0 plus the reduction potential equals 3.34 volts, which is to say that the standard reduction potential for copper is going to be 0.34 volts. So the reduction of copper is known to have a 0.34 voltage, but it's relative to the standard hydrogen electrode. If we use a different reference cell, if we decided to use some other half reaction as a reference, this value would change and everything else would change. And that's why I have here as an example, what if you decided to use Mount Everest as a reference for your elevation? Are you any longer going to be at 7,500 feet if you're in Alamosa? No, you're now at some negative 20,000 feet or so, okay? And so if we're considering a different reference, we change all the voltages. But what we're going to use is the standard hydrogen electrode, which we're going to consider to have 0 volts, and compare all other reactions relative to that, okay? So we're now just have to start enumerating our tables to figure out what all these different half cell potentials are relative to the standard hydrogen electrode. And you can find in the back of a book where we have plenty of these standard reduction potentials, and they're all measured to the standard hydrogen electrode. And so let's take a look at another reaction in which the hydrogen now is going to be the one that is being reduced, so it's at the cathode, and the anode being zinc. And let's determine how we can find a reduction potential for zinc when in fact in this reaction we see it as being oxidized. So we look at the sum of those two reactions, we get the overall cell reaction there. And then we want to determine this standard reduction potential of zinc. So if we were to measure the cell voltage between those two, after we set up our galvanic cell, we'd find a cell voltage of 0.76 volts. And so since we've already assigned that the hydrogen half potential, whether it be oxidized or reduced, is going to be 0 volts, since it's the one being reduced here, we can just plug in a 0 for its value. And all we're left is the oxidation half potential, and then that must be what is giving us the 0.76 volts. So we know what the oxidation half potential is for this, okay? But what we want is the reduction half potential. And when I look at those, that reaction, the oxidation half potential pertains to zinc going to zinc 2 plus 2 electrons. Well, the reduction half potential is just the backwards of that. So it's zinc 2 plus 2 electrons going to zinc. So if we're looking for the reduction half potential there, we just have to give multiply by a -1, we get negative 0.76 volts, and that's a reduction half potential. So we just flip it, just like if we were to flip a reaction when we were doing, when we were looking at solving for delta H's and so on, we would also flip the sign there. And that's the same thing that we're going to do here. We can flip the reactions, but we also have to flip the sign that's associated with it. So the reduction potential becomes a negative of the value of the oxidation potential. So we can look at all these reactions. You see sort of hydrogen sitting there sort of closer to the middle, but all these reactions are measured relative to hydrogen. And so that's why it's given that 0 volt value, and everything else is just relative to that value that we're seeing there. And we realize that if we're talking about something that has a greater voltage, that is something that is going to help delta G be negative. So that means that it is a stronger oxidizing agent. If we go look towards the bottom of that chart there, then those things usually are indicative of something that doesn't want to go in the reduction direction. It wants to be oxidized. And so those things are typically our stronger reducing agents if they're lower than the hydrogen that you see there. So here is a question that gives you standard reduction potentials, and it says which is the strongest oxidizing agent, okay? So there's a couple questions we want to ask to make sure that we get things straight when we see that. And if we say strongest oxidizing agent, then we know we're saying that it wants to be reduced. It really wants to be reduced. And so all that's asking, remember delta G is negative in Fe, so if something has a really large E, then it's going to help for delta G being spontaneous. And so if we want a strong oxidizing agent, we're looking for a really large value for the reduction potential. And these are all reduction potentials that we see above there. So we just have to look for the biggest value, and that's going to be bromine in this case. This question says, what is the strongest reducing agent? And so if we're looking at strongest reducing agent, we still have to go ahead and we should think about that argument in terms of this is what wants to be oxidized the most. And so that means that it's got the largest negative reduction potential. So what's the largest negative number there? And the one that we see is aluminum. So aluminum is our strongest reducing agent in this case. Okay, so let's see how we can use standard reduction potentials. So we can now go ahead and just take a reaction of, say, zinc being oxidized, and we could take copper being reduced, and we have both of those standard reduction values, reduction potentials for both of those. And so what we're going to find is that, yeah, we had a chart of all these reduction potentials, but remember the oxidation potential is just the negative value of that. And so if I go look up on zinc, I'll find a value of negative 0.76 for its reduction potential. But I know that we're looking for the oxidation potential, so that's 0.76, a positive value. And for the copper, we'll just find 0.34 volts because it's already in its reduction potential form. And we go ahead and sum those two, and we end up with 1.1 volts. Okay, so we can figure out what the cell potential is for these reactions that we might not have even done, just because we know what their standard reduction potential is. I know that if I make a cell, I can hypothetically make all these different cells, and I can already tell you what the voltage would be between them in their standard states. Another one that is good to look at is we have silver being reduced here. And so we don't have to change anything there. Just look at the table, you'll find 0.8. We have copper being oxidized, and so that's going to give us a value. When we look at the reduction potential, we get 0.34 volts. But since it's oxidized, we have to flip it, so it's negative 0.34 volts. And then we sum those two, and we end up with 0.46 volts. And now I know the voltage I would expect by putting those two in a cell together, or in a galvanic cell. Another important point I want to notice is that we multiplied by 2 for the whole reaction of silver. Well, because this is an intensive property, you don't multiply the voltage of the reduction potential by 2 like we used to do with the delta H's, delta G's, delta S's, and so on. In those cases, when we were summing reactions with those state functions, we would always, if we had to double, triple the reaction, if we flipped it, well, you do have to flip it here, you do have to flip the sign, but if you double or triple it, it still stays the same value, okay? So you don't have to multiply by whatever you use to balance this out. Okay, so let's look at a spontaneous, what the spontaneous reaction we would expect if we have zinc and aluminum 3 plus. So if I give you the standard reduction potentials of both of those, we get negative 0.76 for zinc 2 plus, and negative 1.66 volts for the reduction potential for aluminum. So if we look at that, which reaction is going to be favorable? Well, if I go ahead and do the aluminum being oxidized and the zinc being reduced, I'd find a cell potential of 0.9 volts. Now, if I flip the other one and say that the reduction for aluminum is what's occurring and the oxidation is for zinc, we get negative 0.9 volts. So which of those two is spontaneous? Well, remember delta G equals minus NFE, and so we're looking for the largest positive value in order to find the most spontaneous reaction, and so that's the top one there that we see. So if we're trying to find this reaction's cell potential, we have zinc plus 2 electrons going to zinc solid, and then we have aluminum going to aluminum 3 plus 3 electrons. That's what we expect there. Of course, we do need to balance this first because we have 2 electrons on the top and 3 on the bottom. So we have to multiply 3 to everything on the top. That gives us 3 zinc, 6 electrons, 3 zinc solids. We'll have to multiply by 2 on the bottom reaction there. And so that gives us 2 aluminums on both sides and 6 electrons. Notice I didn't change the values on the right because we said we don't multiply those in this case with cell potentials. We look at the sum of the reactions there, and the cell voltage would be 0.9 volts as we predicted above. Okay, so let's look at this galvanic cell that you see here, and it says if these things are in their standard states, determine the standard cell potential. So we have basically, so you know you have to flip one, and that could be either the lead reaction or the silver reaction. And so I just start flipping, and I'd say maybe flip the lead first, and that gives you a positive 0.13, and then add them. And so that gives me 0.93 volts, a value that should be spontaneous. Okay, so that I'm leaning towards being the answer, right? But maybe I'll check the other one first. So the lead, I keep the same way, and so it's negative 0.13. And now I flip the other one to become um, the oxidation here. And so I get negative zero point 0.8 volts. And so that gives me negative 0.93 volts. We know that we shouldn't get a negative potential, and it's not even a choice up here. So we should expect that that 0.93 volts is correct. What they're trying to trick you on here, though, is are you multiplying by 2 to balance out the electrons and multiplying the E naught? That you shouldn't be doing that. Remember, you just add them. You don't multiply to balance out. And so we should get that 0.93 volts. Okay, so this one says we have an electrochemical cell and we have these two half cells present. Which one's going to be reduced spontaneously? So if we put these together, which one's going to want to be reduced? And so again, these are both reduction half potentials. And so we have to flip one of them, right? And so you can flip either one first. If we wanted to flip the first one, it'd be negative 0.96 plus 0.34. And that should give us, a negative 0.62. And so that's negative, right? That should not be spontaneous. So it wasn't favorable to flip the first one. Now, if we flip the second one, then we get 0.96 minus 0.34, and then that's just going to give us 0.62 volts. That's a positive value. And so we should suspect that if that's the case, then what we want is the copper to be oxidized in this case. And so the species that's reduced spontaneously should be the nitrate. So that is A in this particular problem. Okay, so that was looking at cell potentials under their standard conditions, right? But as we've seen when we've looked at the reaction quotient and other things, reactions they're not commonly at those standard potentials. So we want to be able to define it for any other conditions that are present. And we know already delta G equals delta G naught plus RT ln a Q. But now we have this other term. We know that delta G equals minus NFE. If we're talking about the standard state, it's delta G naught equals minus NFE naught, right? So we can go ahead and plug those values in if we'd like for delta G's here. And so what we can do is simplify that by dividing both sides by the NF, and we end up with a value of E equals E naught minus RT over NF ln of Q. We can make this a little bit different by just changing that natural log into a log base 10. And so if we do that, there's just a relationship that a natural log is equal to 2.303 times the log of whatever was the argument there. And so we can just switch that out for being a log if we want and have a log base 10. This used to be more favorable in the past when log base 10s were easier to use, but with calculators, that's not too big of a deal. And so at 25 degrees Celsius, we could then plug in a temperature value, and we already know what R is. And so F is a constant as well. So we can basically calculate RT over F for the temperature of 25 degrees Celsius, and we get a value of 0.0592 volts over N, or the number of electrons exchanged in a particular reaction. And so there's the reaction in a little bit more detail, or the simplification of that if you want a little bit more detail on that. So let's take a look at using that Nernst equation to calculate the cell potential of something with ion concentrations not at the standard values of 1 molar and so on. So looking at this, we have to first figure out what the cell potential is on the standard state. And so we do this just as we've been doing before. So we take copper reacting to copper 2 plus 2 electrons, and there's its oxidation potential. And then the iron plus 1 electron, the iron 3 plus 1 electron to go to iron 2 plus. That doesn't balance out with the electrons, so I already took the liberty of multiplying it all the way through by 2. And so then electrons balance out. We can add those two half reactions, and we get the cell potential of 0.43 volts is what we're looking at. So that's a spontaneous reaction we're looking at there. So the value for N should be 2 in this case, and we can calculate Q by just looking at that final reaction there and looking at what the reaction quotient should be, plugging in all those values, I get 1 times 10 to the 6. I go ahead and I take my E cell equals E naught minus the 0.0592 volts over N, which is 2, times log of that reaction quotient. Plugging in all those values, we get 0.26 volts. And so notice the cell potential is a little less than it would have been if it was at its standard state. So it's a little less spontaneous at those current conditions. So this is how we would use that.